No, it's okay. You just met your mom's home. All right, let's talk about friction. So what is friction? Well, it is a force. Most of the stuff you already know. I'm just sort of formalizing it, and I'm introducing you to a new concept as well. So friction is a force that resists motion. It involves objects that are in contact with each other. So when something slides across the floor, a car comes to a stop. What about something gliding through the air? Because it's air resistance, right? So really what you've got there is you've got the particle, whether it's a ball or whatever, in contact with air molecules, right? So there has to be contact. Now, what about, like, what causes friction? Well, there is a theory about friction, fairly well developed, but there's still some research being done on friction. It's not thoroughly understood. It's on that scale moving towards a robust theory. So they believe, and again, this is out of that handout there, right? So they actually believe that objects deform surfaces, right? So like when you put something on a table or whatever, right? The water bottle sitting here actually makes a little whole little impression, and when it's pushed across, right, it actually has to go uphill, doesn't it? Right? So that's one hypothesis, one thought. The object deforms the surface and vice versa. A plowing force is required to move the object over these deformations, or has to go uphill. I guess a plowing force is really sort of uphill. And again, like, not a lot of this is important. I just sort of lay in the groundwork here, right? I'm not going to ask you what kind of force is required to move the object over deformations. I'm not going to ask that. They believe that irregularities interlock and offer resistance to movement. So there we're talking about how the surface is not perfectly smooth. Right? Like it's like that, right? So there's little sort of bumps and things, and they hook together almost like Velcro. When you're sanding wood down in the wood shop there, what are you doing? Yeah, you're taking off little bits, right? Like you're smoothing it out. There is some thought that the smoother they get, obviously it's going to get slipperier the smoother it gets, but at some point they can get so smooth that the friction actually increases. What do you think about that? Why would that be? There's a couple different things that come to my mind. They're actually, now this, because like that, when they're sort of like not perfectly smooth, there's some space in between, right? But now they're so smooth, they're so close together that the molecules are actually attracted to each other, right? Yeah, it's like not even two surfaces, it's more like almost one, yeah. The other thought is there's sort of a vacuum effect happening. There's no air in between, right? So there's some of that vacuum effect as well. So anyways, I mean, not a huge deal. It's there in that handout if you need. Okay, this you do need to know though. Okay, and that is the idea of starting friction. What is starting friction? It is the maximum frictional force between stationary objects. So things that are at rest, the globe sitting there. If I go over and I push on it, it is starting friction that holds it in place. And it's all in the hand again. Should be. Somewhere. and starting friction is the maximum frictional force. Maximum. It's sometimes called static friction. Static means at rest, not moving. Static electricity, right? Charges that don't move. Sliding friction, sometimes called kinetic. The frictional force between objects that are sliding with respect to each other. Sliding friction. And it is always less than static. Oh, got it the wrong way. No, kinetic. Kinetic friction is less than static friction. Are we good here? Okay, so when I say properties of friction, what does that mean? What does properties mean? I don't mean like they're playing Monopoly and they own like Park Place. The characteristics, yeah, things to know about friction, I guess. Yeah. Okay, you probably found them in that handout there if you're looking. The first one is that friction acts parallel to the surfaces that are in contact. So parallel is sort of a key word. Friction is parallel to the surfaces that are in contact and is also in the direction opposite to motion of the object or to the net force tending to produce such motion. So in other words, it's opposite the motion. And if there is no motion, well, it's opposite the force that would cause the motion, right? Like FA, friction is opposite the motion. And it's parallel to the surface. Okay, another property of friction is that it depends on the nature of the materials in contact and the smoothness of their surfaces. The smoother the two surfaces are, the less friction there is, right? Like ice, exactly. Right? What do they put down on the icy roads in the wintertime? Sand, gravel, to increase the friction, make it less smooth, right? Yeah, salt to melt it, I guess. But they usually put gravel down, gravel and salt mixture, right? To make it a little bit rougher. There always has to be two surfaces for there to be friction, right? Like you can't just say like, what's the friction on ice? It's always going to be like, you know, like Teflon on ice, right? Or steel on ice. Lawson knows the difference between different sliders, right? What's the difference between a Teflon slider and a stainless steel slider? Stainless is quicker. What does that mean? Less friction, right? Stainless steel sliders are crazy. I used one once. Yeah, you can go pretty much the whole way, right? Yeah, there. Yeah. Go a long way on a stainless steel slider. Slide it into the DM. Okay, I think, whoopsie, that's not what I wanted to do. I think you guys know, I wrote this on the previous one, right? Where I said kinetic is less than static, I think, right? So same idea here. Sliding friction is less than or equal to starting friction. So again, if you want, sliding friction, that's kinetic, right? You got this already. Kinetic is less than static. It always is more friction at the start. Here's a controversial one. Friction is practically independent of the area of contact. The idea is this. I used to get a textbook to show this, demonstrate this. Would you agree that the spine of the book is the same material as the back of the book? Yeah. Right? So the amount of friction when it's like flat like this, Travis, show me where you draw hiding that. The amount of friction right here is the same. Oh, it just seemed to be like you're in the classic texting pose. Hands down, eyes down. Sorry, man. You're in classic texting pose. Yeah. Okay? The amount of friction would be exactly the same as if it was up on end like this. Same amount of friction. The amount of area of contact doesn't matter. It's only the force down. So again, friction is practically independent of the area of contact. And the last one here, starting or sliding friction is directly proportional to the force pressing the two surfaces together. And I'm going to spend a couple minutes explaining this as well. Starting or sliding friction is directly proportional to the force pressing the two surfaces together. So what I'm saying there is this. Usually on a flat surface, if you've got an object, right, you've got the weight force down, and what's this force up called? Normal force, right? And generally they are equal to each other, right? And the amount of friction is dependent upon how much force that is. They're going to be equal numerically, opposite direction, right? Now, what if I were to be, like, let's say that this is like a lawnmower or something, and I'm kind of pushing down at an angle. Well, I'm pushing it sideways. I've got that FAX that we talked about before, right? That horizontal component. But not only am I pushing sideways, but I'm also kind of pushing down. And by pushing down, What would you call that? FAY. It's the y component. Right? And by doing that, I'm kind of increasing the amount of force down, right? Right? Is that going to make it harder or easier to slide? A lot harder. It's pretty easy for me to push the scale around, right? But if Zach jumps on there and pushes down, it's going to be a lot harder to push. What's changed? The amount of friction, right? He's changed the amount of force down. So the friction is increased. And the same is true. What if instead of pushing down, what if I were pulling up? Like so. Well, then you've still got your FAX, and now you've got your FAY, but now your FAY is up, and now that big heavy object is actually easier. Well, it's lighter, feels lighter, right? It's easier to push, isn't it? There's less friction. Because this friction is directly proportional to the force pressing the two surfaces together. And this leads us to the key idea for the day, which is the coefficient of sliding friction. And Josh is going to make fun of me again. The coefficient of sliding friction is the ratio of the force of sliding friction to the normal force. So sliding friction over the normal force is known as the coefficient of sliding friction, or just coefficient of friction. Or sometimes they say frictional coefficient. Okay? So the frictional coefficient is really, it's a measure of how much friction there is. It's a measure, it's a number. And it comes with its own special formula. And it's a defined formula. The coefficient of friction is the Greek letter mu divided by, or is equal to FF over Fn. I looked hard, Josh. I couldn't find. All I saw was. So it's FF over Fn. It is the Greek letter mu. It looks like that. It's a U with kind of a tail on the front. Just a different letter from a different alphabet, that's all. Now, what are the units for this mu value? What are the units, like meters per second or centimeters or what? Like what the heck is it? Well, FF is measured in newtons, right? And Fn is also measured in newtons, which cancel out, and the answer is there's no units. It is a ratio. There are no units. It's newtons per newton, which is nothing. Nothing. No units. There is no units. Got example 1 on a sheet? You need that formula. Mu equals FF over Fn. Alrighty, so you should have this example. There's 3 of them to do. I'll bring you along with this here. A box with a mass of 175 kilograms pulled along a level floor with a constant velocity. If the coefficient of friction between the box and the floor is 0.34, what horizontal force is exerted in pulling the box? Let's have another reread. A box with a mass of 175 pulled along a level floor with a constant velocity. Now, what does that say when the velocity is constant? There are forces that just add up to 0. The net force is 0 because the acceleration is 0, which means the forces are balanced. What coefficient of friction between the box and the floor is 0.34? What horizontal force is exerted? So this is the applied force, right? What horizontal force is exerted in pulling the box? They're asking for how much force is on the object. What's the applied force? We got FA, we got FF, they're balanced. We got weight force, and we got normal force, and they are balanced. Virtually always, the first thing to do is to convert the mass to newtons. Okay, by taking the mass times 9.8. So 175 times minus 9.8. $17.15. $17.15 newtons, right? That's down, right? Okay. Now that means then that the normal force is 17.15, right? It's up. Okay, so when I go, what horizontal force? I'm looking for FA. To get FA, I'm going to have to find out what FF is. How am I going to get FF? Well, I have the normal force and I have the mu value. So I can now write mu equals FF over Fn. Remember, just the coefficient of friction between the box and the floor is 0.34. 0.34. We're going to solve for friction, and our normal force is 715.15. Now, a little off topic here, but I wrote a letter to Santa, and my request this year is for all my students to know how to solve these problems without making any mistakes. I've been pretty good this year, so I'm hopeful. How do we solve this? You multiply, right? This is attached by a divide by, so we're going to multiply. So FF is going to be 0.34 times 1715. And you get, oh, that number's crazy big. 0.34 583.1? 583.1, right? And since we've already established that FA and FF are equal to each other, right? Therefore, our applied force is 583.1 newtons. Now, actually, this FF here is actually negative. How come? Because it's really left. Now, note that, please note that this negative doesn't come out of your calculator, does it? Right? It's not going to come out of your calculator. You have to assign that value. How come? Because it's to the left, right? Your calculator is not always going to give you that number. Don't think about negatives as sort of the number, but as rather the direction. So did I answer the question? What horizontal force exerted in pulling the box? Yes. Okay, so probably like 1, 2, 3 steps, right? Because it's to the left. Are we good? Yeah? Okay. 2 more to go. This time we have a box of mass 100 kilograms. It's accelerated. Oh. not a constant velocity. It's accelerated by a force of 200 newtons across a level floor. If the coefficient of friction between the box and the floor is 0.2, what is the overall acceleration? We are solving for A. We're solving for A. Let's draw our picture. We got weight force, we got normal force. They're balanced. This thing isn't going up or down. We have 200 newtons is our FA, and we have some value FF that we don't know. What should I do first? We're gonna convert that 100 kilograms, that mass, to newtons. So FW is equal to mg. Minus 980, right? Which makes our normal force equal to positive 980. Sometimes the question people, those naughty question people, they like to give you the weight force already in newtons. They've already multiplied by 9.8. Every once in a while they do that. They'll say the weight of an object is so many newtons. Do not multiply by 9.8. Okay, now with my Fn, and this time I have my mu, I can solve for friction. Right? The mu value is 0.2. We're going to solve for FF. What's what? 980. 980. So I got 0.2, mu equals FF over Fn. The 0.2 is my mu. I'm solving for FF. My Fn I've just figured out to be 980. And how do you solve this? Multiply both sides by 980.
Yeah, 196.
And take 980 times 0.2, that's right. 196?
Yeah.
But it's negative because it's to the left. And now, right, we're trying to find the net force here. So now I'm going to go F net is equal to FA plus FF. My applied force is my 200. And my friction force is minus 196. So I get a measly 4 newtons of applied force. So much friction. It's very rough. Looks like having bus duty all week in minus 38. That kind of rough. Now we can go F net is equal to MA. What was the mass? 100? Yep. Way up top here. Accelerated by a force of 200. And that's going to be meters per second squared, right? Okay, let's have a look here at example number 3. Last one. And I'll give you some time to work. Now this one is going to be the most challenging problem you've seen all year.
No way.
Okay, so time to refocus. Hang in with me for about 8, 9, maybe 10 minutes. If you've got a phone conversation going on, say to them, I need to pay attention. Don't talk to me. I'm busy. Okay, you can last. A box with a mass of 46 kilograms is pulled across along a level floor at a constant speed. What does constant speed mean? No acceleration. Forces are balanced by a rope that makes an angle of 30 degrees with the floor shown. If the force on the rope is 260 newtons, what is the horizontal component of this force? Now, we've talked about horizontal components before, right? So, I'm not calling it FH anymore. I'm calling it FAX, the X component of the applied force. And then what is the normal force and what is the coefficient of sliding friction? Okay. You will notice that I have weight force. I don't think you have the picture, am I right? Right. Okay. So we've got an applied force up at an angle. We got a weight force down, and I think I've neglected to put the normal force on there. You should. Oh, yeah. That is a great question, Kaylee. Kaylee's asking, is the FW equal to the FN?
Yeah. No. Yeah. I'm not the same way.
I don't want to answer that just yet. They are balanced, that is true. But keep in mind, okay, well, first of all, let's deal with part A. Okay, let's deal with part A first of all. Part A says, what is the horizontal component of this force? So that's actually pretty easy. I think I've already shown you this. FAX, right, in this triangle right here, right, grade 9 trig, the FAX is adjacent, right? And which one of the three trig formulas has adjacent in it? Cos. So FAX is going to be FA cos theta. So in this case here, that's 260 times the cosine of 30. Right?
How many decimals do we have to go to?
I usually go one more than what I'm given.
Which is
Well, there's none, so 1 decimal place. 225.2. Yeah, well, but to 1 decimal place, it's 225.2. Okay? So that's the horizontal component. I don't know. Nope. 260 times cosine 30. I'll do it again. 260 times 30. Oops. 260 times cosine. No. There you go, Danielle. Okay, 225, right? Now, in part B, it asks for the normal force. So I hear you guys saying, well, how long do I draw this? Now, way back about half an hour ago, I was talking about lifting something like that. So now, are you lifting here? Is part of that 260 actually lifting this thing up?
yeah.
It is. And so you're kind of doing part of the normal force's job, right? The weight force is down, but you're helping that normal force up. And they are balanced up and down, aren't they, right? And this FAY is in the vertical direction, isn't it? Okay? So I'm actually going to put part B down here because I need some more room. Would you agree? Now, you'll notice here that this came up, right? Where did this come from? I don't think I showed you this, but mass times gravity. So the mass of this object is 46. So this is 46 times minus 9.8, right? This is actually minus 450.8, right? The weight force is minus 450.8. Christine, I don't want to explain this to you later, and I have this feeling that I'm going to have to. Okay? So the FW is minus 450. Now, normally, pun intended, normally, the normal force would be 450.8, but it's not because the Y component changes that, right? Would you agree, you're not going to like this, would you agree that F net Y is 0? What do I mean by F net Y? The net, the total of all the Y forces, right? F net Y, the total of all the Y forces is 0. How come? This thing ain't going up and down. It ain't accelerating up and down. It's just sitting there. right? The net y component is 0. And what makes up the net y component? Well, you got your FW, you got your Fn, and you got your FAY. You have three forces that are acting vertically, up and down. Right? Two of them are up. Raston, you're right. Two of them are up, and one is down. Are the negative signs important here? Oh, yeah. So 0 is equal to, what's the weight force down? Minus 450.8. What's the normal force up? We don't know. What's the FAY? Oh. I haven't got the FAY yet, do I?
Can you just do piece squared plus piece?
You could. You could. I'm going to make myself some more room here. I regret doing this. My FAY, if FAX is FA cos theta, FAY opposite is going to be, yep, FA sine theta, isn't it? The y component is the sine. So this is going to be 260 sine 30, right? $260 times 130. Did you get 130?
Yeah.
And which direction is that? Up. So positive, right? So I'm going to put that plus 130 in right there. So my F net y, my total y forces are my FW, my Fn, my FAY. The FW is down, it's negative. We don't know the Fn, and the FAY is up, and it's 130. And now to get my Fn, I'm going to leave Fn on this side. I'm going to take minus 450.8 to the other side, and it's going to become positive 450.8. I'm going to take that plus 130 to the other side, and it's going to become minus 130. And my normal force is going to be 450.8 minus 130. The normal force is less than the weight force. How come? Because you're lifting up. And by lifting up, you reduce the friction. Am I done? I'm afraid not. One more part, right? What is the coefficient of sliding friction? So we are solving for the mu. Mu equals FF over Fn. We're solving for mu. So our FF is, oh, hang on. I don't know the FF yet. It is equal to FAX. Now, did you write this down already? Now, I want to show you something. Whether you write it down or not, it's up to you. But really, this whole thing that I just introduced to you now, I couldn't do it before because it would have, like, your head would have exploded. You're ready for it today. But really, when we say that FAX is equal to FF, are we not doing the same thing as this? Are we not saying F net X is equal to 0, right? And 0, what's F net X equal to? What's force is making it up? FAX plus FF. Am I not just doing that? Right? Like I'm saying that the net X is 0. Why? Constant speed. FAX and FF are my X forces. And so really I've got 0 equals FAX was my 225.2. You can. You know what? Just watch. Just watch for now. Just watch. Pencils down. Just watch. I'll show you when I'm done. Just watch. I can see I'm freaking you out here. Just watch. Katerina, you watch. Yeah? Okay, so the FAX is 225.2. Do I know my FF? I do not. So I'm going to leave FF here. I'm going to take that to the other side, and what does it become? So all I said, Danielle, it's simple. Just watch. Okay? All I've said is that the FF is equal to the negative version of the FAX, right? But I've just made it more complicated. Okay? Why? Because at some point you might have more than one force left and right. Right? I told you before the Fn and the Fw were always equal to each other. I've introduced a new concept with this FAY, and I've made it a little bit more complicated so that you can solve for it. I'm showing you that the same process holds true for the x's, even when there's only two. We all know that the FAX and the FF are going to be equal to each other, because there's only one each way. But if there's more than one, you're going to have this in your toolbox. Okay? So now I can finally go FF. What is my FF? This number right here. 225.2 all over my Fn, which I figured out to be 320.8. And I get 225. Oh. 225.2 divided by 320.8. 0.70. And now I'm going to wait for the inevitable question. Why is it positive? Mu is not a vector. Mu is a ratio of one force to another. And oddly enough, it's a vector divided by a vector. But mu itself is not a vector. Mu has no direction. And so really, there is no negative here. Now, if you happen to slip up and you put negative in there, I'm not going to worry about it for a while. Eventually, you'll just realize, oh yeah, mu values are never negative. So don't worry about it.
Or it doesn't have a weird mu thing.
Mu. Yeah.
Oh, we don't have any negative answers?
No. No. And in fact, I should tell you this, that mu is generally less than 1. Virtually always, mu is less than 1. If you get a mu value that's greater than 1, either you've made a mistake or I've made a mistake in the question. But usually mu values are less than 1. Okay? That's a pretty big question. Yeah. Should I go through it again, kind of as a step by step kind of thing? I'm not going to write everything down, but should I just sort of explain each step? I'll just do it quick. 2 minutes. So I found my FAX, my horizontal component. I've got my weight force here. I know that I had to find my y component. Then I plugged my y component into this F net y equals 0 because the total of the forces up and down are 0. Yeah, but as I've taught you, showing your work, putting your equal signs all lined up, blocking your steps. If I can see you did the right steps, I'm going to follow it through. You're going to get 5 out of 6. Stop worrying about the final answer. Worry about the process. Now, can you do this without showing your work? No. I hope I've cleared you of that terrible habit. Now, I want to say this to you too. My grade 12s to me this morning, my grade 12 saw some of these questions sitting out, and they looked at these and they went, oh, that was so much easier back then.
Yeah, right.
They did.
Yeah, that is, well, you're literally taking like a T,
Anyway, I got those guys through grade 11 and into grade 12, and they're all going to pass, and I can get all of you guys through it. But it takes practice and it takes time. You will have come a long way by the time I'm done.
100.
Oh, yeah.
John. This is a whole page.
That was one part.
That's not it.